So today I'll talk about the greatest mystery of quantum mechanics, and it is observation. Observation in quantum mechanics. And I'll try to explain that despite 100 years of study, it is still a philosophical problem that people do not know how to treat. And I'd like to discuss it in some detail. And I actually would like to have a discussion session. So I would like to hear your question. So there is an axiom of observation. And axiom of observation is that if we have a physical state and we know that this state is a line, L psi in projective space, and we have an observable, it is a physical quantity, this corresponds to device, observation device, that we call O, then observation is probabilistic. So it means that we get results lambda I with probability raise projector I times projector L psi. Proj I is a projector to the eigenspace corresponding to eigenvalue lambda I of O. Projector L psi is a projector to the line L psi. So it is an axiom. However, the question is, how does it happen? And we will consider example where we have C square over C star, that is CP1, and we will take observables. So observables as being Hermitian operators in C square. And we will consider case. One observable would be T3, and another observable would be what is called T1. So let us take a state corresponding to psi equals 1, 0. It is an eigenstate of T3. So we will get in observation plus 1 corresponding eigenvalue with probability 1. At the same time, if we will observe T1, its eigenvalues, its eigenspaces are, so let us check what are them. This operator equals, of course, 1, 1. These are eigenspaces.
You missed a minus.
Yes, I missed the minus. I was looking for eigenspaces. Yes, I missed the minus. So let me call this plus and this minus. So one can check that that trace of projector plus projector psi, projector L psi is 1/2, and similarly trace projector minus projector L psi is 1/2. So probability that we will get in observation of T1 in the state psi 1 is 1/2 and minus 1 is also 1/2. Thus, first average in observation is 0 in observation of T1 in state L psi is 0. Second, distribution of the observations has a dispersion. So let me remind you what dispersion is. So people know linear algebra, but people not always know probability theory. If we have a distribution, probabilistic distribution, for a random quantity, let me call it Q, we have an average. So what is I? I is what can happen. Qi is the value of Q if event I happens, and omega I is the probability that event I happens. Consider Q square. It's also random quantity, and the average of Q square is similar. So it's sum over I. So I is events. So what can happen? Qi square omega I. And then there is a measure showing how random Q is. If Q is not actually random, it means that in one event, so it means that omega, say 1 is 1 and omega I is 0 for I not equal to 1, it means that only one thing happens. Then Q square equals average of Q square. But in general, for random Q, one may show we have inequality that Q square minus average of Q square is greater or equal than 0. And this thing is called dispersion of Q, and people sometimes call it D of Q, so it is not differential, it's dispersion, not differential. So how can one prove this condition? To prove this condition, it's enough to consider, let me call it D condition. Consider new random variable that is Q minus average of Q. Let us call it Q tilde. So it is just a number. So it is clear that average of Q tilde equals to 0. Okay, but we may look at average of Q tilde square. It's definitely greater or equal than 0. So here we have this minus 2 Q average plus Q average. That gives Q square minus average of Q square. So how I computed this? It is Q minus Q average. I had this thing and I considered an average. So this was this. So dispersion shows how random we are. In particular, in the example considered, the dispersion of T1 on the state corresponding to line passing through the state 1, 0 is the following. Is the average of the square. So square is 1. So it is, this is 1, and this is 0, is 1. So dispersion is really big. Okay, so that is what happens from the point of view of probability theory. But now the interesting question is, what actually happens when we measure observables like T3 or T1? When we measure T3, nothing happens with the physical state. We can continue measuring. However, what happens when we measure T1? And measurement give value, say, +1. We may measure again, and sure, we will get the same value. This is an experimental fact. You may try to understand it. Suppose you have a beam of electrons, and suppose you have a magnetic field. So some electrons go up, some electrons go down. And suppose here is a wall. So if electron goes up, it continues going up. If electron goes down, it continues going down. So how one can measure that electron goes up? We can put here photofilm or any kind of detector. Okay? Now, the question is what happens with the state under measurement. So there is so-called Copenhagen interpretation saying that in the process of measurement, state probabilistic goes into the eigenvalue of the observable. So according to this interpretation, there are two different processes. Process 1, evolution, that is just unitary rotation, and it is deterministic. It means that no probability. Given a state at t equals to 0, we definitely no state t greater than 0. Process 2, strange process of measurement, probabilistic. Psi goes to one of eigenstates, I, probability, omega I. And then the question is, how this could happen? Or what is the difference between evolution and measurement? Maybe, as people in Copenhagen thought observable corresponds to a device that is big, while quantum system is small. Not true, since we observe big quantum effects in lasers and semiconductors. And sorry, not semiconductors, and superconductors. So what happens? And here we will discuss the Schrödinger cat puzzle after the break. But before the break, I would like to hear questions.
Well,
Okay. Okay.
no, go ahead.
You first, please. Okay. Professor, I have a question. As I know little physics, I have a question on why the probability is the trace map, is the trace of some projection, some projectors.
It is an axiom.
Okay. Oh, so we assume it's like
Yes.
this.
We
Okay.
assumed it, and we checked, and people checked it in numerous experiments. It's an axiom.
Oh.
That could not be deduced from anything else.
So you mean we assume it by some observation in some experiment, or just assume without any observation?
So people started making experiments like 100 years ago, and they got probabilistic results, and then they summarize what they got in this axiom. So they made different observations with different devices. These devices, that devices. So full life 100 years ago was full of experiment. They measured coordinate of a particle, momentum of the particle, spin of the particle, polarization of light, this way, that way. And finally they realized, so actually it was Dirac who put it this way, that all measurement devices could be described as Hermitian operator. It was a result of analyzing of many experiments, thousands of them.
And it seems the trace map from the linear algebra is something very weird, something very important, but okay. Thank you.
And finally, they realized after putting it that the probability is just a trace map between these two lines, and it could not be reduced to anything else, to anything. You cannot deduce it. At least nobody knows how to deduce it from something more fundamental.
Yes, we learn a lot of trace map from representation theory from of some groups. I don't know, is there any link between some representation of some groups, which I mean character functions and these probability explanations? I don't know, is there any link between representation of groups and the probability explanation? Okay, that's my question.
So I don't know about groups here, but it is but it is a linear algebra in some sense. Suppose you know that your physical state is a projective line, and suppose you know that your observable is for some reason Hermitian operator. What kind of linear map from Hermitian operators to numbers that would be an average you can get? So actually it is the only possible way to do it. However, despite it is satisfactory mathematically, it is a new physical principle, new physical concept that appeared in the work of Dirac, who said that from all our experiments and from all our constructions, we may have an outline. And this is the outline. Doing something with particles, with spins, with polarizations, everything could be put in this form. So any other questions? Tim?
Yes, I had a question about this experiment with the electrons and the stream of electrons in the magnetic field. So here, I think we should be quite clear on what we consider the state, whether we consider the whole stream to be like a single state or some random electron from the stream, or well, we can't say anything about a particular electron because we haven't measured it yet, but I think that this needs to be a bit more precise, right?
Okay.
Because otherwise it's unclear what it means for it to be probabilistic in the first place. Like we
Okay.
can see the picture
Okay.
where
So
some go up and some go down.
okay. So let us take a particular electron. So we put a magnetic field. Just imagine that electron goes up and starts ionizing detector. We consider the same electron because after ionizing detector, it continues its motion. So I'll try to draw it. So there is something that we observe. So here we have a film. And here we have a film. And consider a single electron. And here is the wall. We have events like this. We also have events like this. However, we never have events like this. Never. So electron continues its motion.
After the beam has been split, yeah, surely it's
So
no
this is the
question there.
picture. This is a picture. What happens if I have a single electron? I put a single electron. I can have this or this for a single electron. And I never have pictures downstairs. It's a single electron.
Yeah, it is clear how to speak about a particular electron between measurements. I mean, somewhat clear in this context. But how do we speak about a particular electron between the emitter and the first detector in that region where the beams splits? There seems to be no, well, if we don't track the electrons there, if we don't have many sensors along the way, then there is no way to speak of particular electron, and drawing the trajectories of the electrons as you have done above.
It is not, yes, it's not.
It suggests a classical picture.
Yes, so I agree. So I agree. I agree. So you say that here we have an emitter, here we have a wall, here we have these things. So electron somehow goes here. And here we have magnetic field. So in some sense, electron goes. You are right. We cannot write classical trajectory. Before electron start interacting with the detector. So here, no classical trajectory. When it hits, here we have it. So thank you. This picture was what one would expect. So something happened. Okay, so the problem in Copenhagen interpretation was that physical reality was divided into quantum system and classical device. But device is or should also be considered as quantum. So here we need an extra concept. Suppose we have a system 1 and system 2. What are so system 1, suppose that system 1 is determined by CP and 1 minus 1, and system 2 is governed by CP and 2 minus 1. Then when we have system 1 and system 2 together, their space of states is CP and 1 plus and 2 minus 1. By definition, almost system 1 and system 2 is also a physical system. Okay. And here Schrödinger formulated a Schrödinger cat puzzle. Suppose we have the following system. We have electron. We have magnetic field. Here is a wall, and here we put a bomb. And here, near the bomb, we put a cat. And all this is a lab. And here we have a door. And here we have a person who wants to see what happens. So we start with the state of electron. Let us start with the state of electron like this. And then electron goes this way. In magnetic field, we have this thing times electron that goes up plus this state, and here electron that goes down. So this is the starting position of electron.
And by that ket, you mean the
actual ket?
No, by the ket vector, you mean the position function, the wave function without the spin, right? By the ket vector start up or down.
So ket is an actual ket.
No, I mean the ket vector, K-E-T.
Ah, Yes, ket vector. Yes, yes. So by ket vector, by this vector, I mean position of the center of mass of electron. It starts moving, so it is somewhere here. It's a starting position. Then in magnetic field, yes, then in magnetic field, it is 1, 0 times going up, 0, 1 times going down. So this is the result of unitary rotation. Then what happens? We take this 1, 0 times up plus 0, 1 times down. And here we multiply it by a bomb. That I will write it as a quiet bomb, and then ket. What happens then? Then in the process of evolution, if we go up, we have 1, 0 times up times exploded bomb times no ket. If bomb explodes, there is no ket. Plus 0, 1 times down times quiet bomb times ket. So system in the lab is a kind of superposition of a ket and a dead cat. And how this could be is a puzzle, because humans would not imagine such a state. People used to say that either we have a cat or we do not have a cat. So it is actually a question where probability comes from. So is it a cat who enters probability in the system, in the evolution? And it was actually John von Neumann who put it further. He called this psychophysical, both is psychophysical parallelism. I will not write these words. And it was developed later by Everett. And the idea is the following. Let me come to this picture. Just imagine that no probabilistic things happen. That when physicist opens the door, state of physicist also splits. So he says that we may continue this by adding here a physicist. So I will draw physicist as a face. So he doesn't know what would happen. And here,
I think it's better to copy it or write it once more, because I think it will be very confusing.
Okay, thank you. Thank you for good advice. Okay, so I add here a physicist. At the moment, physicist doesn't know what would happen. But then you will have the following situation. Physicist who is sad because no cat. And here physicist who is happy because cat survived. So what happens? So you may consider this the state of the world. So according to a unitary rotation, the state of the world turns into a sum. So a sum of two vectors, happy vector and sad vector. In this case, sad vector and happy vector. And suppose another physicist comes. If another physicist comes to see what is going on, we would get blah, blah, blah. So I draw here for the second physicist to show that he is another person. Plus, and if physicists start to talk to each other, they would agree on how do they see the world. Here, they would agree that world is sad since the cat is dead. And here they would agree that the world is happy since cat is alive. And there will be no contradiction from their perception of reality. And such phenomena is called multi-world interpretation of quantum mechanics. It says that probability comes from human beings. It comes from our perception of the world. So, if it is like this is an important thing for our life, really. We as a human beings have not one, but many futures in the world. All possibilities realized in the physical world. How can we control our future if it is probabilistic? In future, in the real world, there are all future. Who we are, who would we be in future? This or this, we don't know, and we cannot determine it. In particular, first, human beings cannot die in their own perception, since there is always a possibility that they survive. It is a miracle for others, but the only way for them. So here we come to the concept of guaranteed miracle. Point number 2, suicide is meaningless. So it's a consequence of one. Point number 3, question. Are we responsible for all worlds, for all futures that we created? Note that futures do not intersect and do not interfere with each other. Suppose I'm a crazy physicist who made this experiment with a cat, okay? Suppose I made this experiment, then am I responsible for killing a cat if it happens that I don't see cat inside? So what would be if I'll just go to the same room with the cat? So let me put here this crazy, so let me put here this person with, okay, maybe it's better to redraw it, no? So what happens? This would be the second physicist, and here I put the first physicist without her. So the question is, would be person like this creating this crazy experiment, what? Guilty for the death of the cat in future, if he would never be there. So here we are coming to the question of quantum moral that is different from classical moral. And all this only because we say that the world is ruled only by unitary rotations. So once again, what is the origin of probability? Is that we as human beings have different futures in deterministic. So it's not the world is probable. The world is deterministic. We have different futures. So this is, I will call it, relativity of probability. And this topic is rarely discussed in quantum mechanics courses because it's actually a philosophical topic. And from my point of view, humanity is not ready to probably discuss it. In order to discuss it, we should, so there should be either physicists who are great philosophers or philosophers who understand physics. So it was put like this in 1959, Everett, and people just don't know what to do with it. So that's why I left like 10 minutes for question, because it is really strange. When I was studying quantum mechanics, I wanted to discuss it with my teachers, but the response was shut up and calculate. Tim, have you thought about it?
Well, about connected problems, yeah. In my view, I don't have a very clear understanding what separates human beings from just very elaborate inanimate objects. So
Nothing.
well, there's this idea that like there's this perception. So I'm not quite sure that this perception can be just thrown away. But in a way, if we consider human beings just as very elaborate collection of atoms, then I don't see the difference between human beings and the world. So I can't.
There is no. The difference is that human beings have memory, and it is in perception of human beings how human beings are seeing the world. So, in particular, so once again, let me do experiment a bit differently. So this could be said world, said system. And here we have said human being. And say coefficient here would be alpha plus beta happy system times happy human being. What is it? From the point of view of human beings, so it could be, say that alpha is like 1/10, something like that. And beta is of order of 1. So what is it? For human being, system could be either sad or happy, because it's a structure of the tensor product. So from the point of view of human being, can be only in the eigenstate, say sad or happy. That's what happens. But in the future, we have this projective line that goes through this linear combination. And somehow the norm of, say, sad component is the probability that our future would be sad. So that's why Schrödinger puzzle turns out not to be a puzzle, not a bug, but a feature. Okay, so that's what I wanted to tell you about philosophy of quantum mechanics. And next time we will come to mathematics. So we'll say something more about mathematics of quantum mechanical systems. So I devoted only one talk to philosophy.